potential energy. I'm going to introduce a new concept, which is a conservative force. A conservative force does work defined as F of C dot ds. This sign means a closed path of integral. For example, if an object starts from point A and goes somewhere under, let's say, a couple of forces, but one of them is conservative force. So if it starts from A and goes somewhere and end back to A, this is called a closed path. So this circle means the integral is about a closed path. If the work done by that force for a closed path equal to 0, and we define that force as conservative force. So what's that for? That is very important because in physics 1A, actually there is only two conservative forces that we need to consider. One is gravity. The other one is elastic force. I can give you a very simple example of friction. Well, work done by friction obviously is, first of all, is negative. Second, it really depends on how far that object traveled around the path. For example, if I start from point of A and goes to point of B, if this is the object, if there's a dragging force, but if I only think about the kinetic friction, F of K, now since displacement from A to B is S to the right, and then work done by kinetic friction equals to force times displacement times cosine, the angle between displacement and Fk is pi, that is negative Fk of S. Can you imagine that later when this object start from B, go back to A? So if it start from B, go back to A, then displacement is to the left. When that happens, Fk will be to the right because kinetic friction is always at opposite direction of the motion. If motion is to the left and the kinetic friction will be to the right. So for the second part, B to A, work done by kinetic friction again will end up the negative Fk times S. So even though we start from A, we go to B, we come back to A. This is a closed path. The total work done by this kinetic friction is the work done from A to B plus B back to A. It does not equal to 0. Obviously, that kinetic friction does not qualify for the concept of conservative force. However, on the for the gravity and elastic force, I can show you that it actually qualify as this definition, that work done by gravity for a closed path equals to 0. Same happened to the elastic force from the spring. Let's think about this force. Gravity. Gravity, well, if we consider a case near the surface of the Earth, and gravity can be expressed as m times g because only near the surface of the Earth that gravitational acceleration is a constant. The value is very close to 9.8 meters per second squared. Now, let's say this is ground. Somehow the object starts from point A. This is the height of HA. And then the object goes to B. It has a height of HB. So let's consider a path. First from A to B, and then let's choose a point C. C and A are at the same height away from above the ground. So what we're going to do is start from A, goes to B, then B goes to C, and C back to A. This is a closed path. So we're going to do that A goes to B, B goes to C, C back to A. And let's calculate what is the work done for this closed path by gravity. Now obviously an object starts from A goes to B and C and back to A. Besides of gravity, there must be other forces, at least one more force. Otherwise the object will simply fall from point A and down to the ground. It's not going to travel like that way. So, but we don't care. We only care about what is the work done by gravity for this closed path. So we say, okay, work done by gravity from A to B equals to force time displacement, displacement is AB, time cosine of the angle. What is the angle between A to B and gravity? Well, gravity is always down. So the angle, cosine of angle, actually should be cosine of that angle. Let's make cosine theta of that one. Okay. So cosine of theta, then we have work done from B to C. That is gravity time B to C. Now during B to C, gravity has the same direction as the displacement B to C. So that is cosine of 0 degrees. And then from work done from C back to A, that is force time displacement, that now CA cosine, and this time C to A is horizontal and mg is vertical, so the angle is pi. So obviously the last one, WCA equal to 0. WBC is simple. Cosine 0 is 1. But what is the first one? Now let's take a look. As a matter of fact, we have this AB. This is A, that's B. And gravity is this way. If we extend this line. So as a matter of fact, the angle theta is angle theta of cosine theta of that one is negative cosine of that one. That is, let's name it alpha. So we can replace the cosine theta, the cosine theta by negative. Well, we still have mg, so it's negative mg AB of this one can be replaced by negative. So cosine theta is negative cosine alpha. AB cosine alpha, look at this equation. AB cosine alpha give us this. This is actually the difference of the height B and A. So as a matter of fact, that will be, if we replace that this term and end up as BC. So if we add all three terms, sigma Wi equals to 0, isn't it? Because the first term is negative mgbc. The second term is positive mgbc. The last term is 0. So the total work done is 0. Therefore, gravity, in this case, obviously, for this closed path, the work done by the gravity is 0. And in this case, gravity seems like a conservative force. We can use many other examples to prove that gravity is a conservative force. Let's look at elastic force, negative kx. This is a spring constant k, and the block has mass m. Right now, the location is x equal to 0. Imagine that we move the block to somewhere here. Let's say this is 8 meters away from the origin. So this is x-axis. So right now the location is right here is x equals to x of a. That's a meters away from the origin. Well, and then if we let this block somehow goes to another position, which is on the left side, let's name x equals to x of b, and this is x equals 0 line. So obviously that is that much, and this is this much, x of a, and that is x of b. Okay. If we ask this question, what is work done by the elastic force when the object starts from, let's say, x equal to xa and goes to x equal to xb? Now, probably you will say this is not a closed path. Don't worry about it, because we're going to work out what is the work done from A to B. Then later we will let the block go back from B to A. Okay, so we finish one complete path. So we're going to do the calculation. We say that work done equals to f dot dx integral. Now, the elastic force is always at opposite direction of the displacement. When the displacement is positive, that kx force is negative. When the displacement is negative, that kx force is positive. So when f dot dx, it will be negative of magnitude is kx of dx. And we start from x of a and goes to x of b, right? So the result is negative, k is constant, x dx is 1/2 x of square from x of a to x of b. So the result is, well, first minus second term. So it is 1/2 kx squared. The second term is positive because minus a negative sign is plus. And the first term is negative. The first term is 1/2 k of xb squared. So the work done by elastic force from xa to xb is this. We can simply ask, what is the work done by the elastic force from xb to xa? Isn't that true? We just switch x and a and b, because before, you see, a is here, b is there. Now b is here, a is there. So the result is 1/2 kx squared. When you see a, you replace b. X, this is b, minus 1/2 k. When you see b, you replace by a. So when we finish a closed path, that is from A goes to B back to A, we just simply add 1, 2, 3, 4, all 4 terms together, and that comes out, and the work done by elastic force equals to 0. So elastic force is a conservative force. Now, we know that gravity and elastic force are conservative forces. Next, we say work done by a conservative force is related to a change of potential energy, and we postulate that work done by conservative force equals to the negative change of the potential energy. So let's look at this case again. If we start from A and goes to B, and A is how far above the ground? B is also how far above the ground, which is HB. This is HA. Okay. Now, we can let our object directly go from A to B. So the work done by gravity, which is mg, equals to mg of AB cosine, and we learned that, right? It is the angle between the AB direction, A to B direction, and the gravity. That is the angle of beta. Angle beta equal to negative angle of cosine beta. Okay, this is cosine beta. Cosine beta can be replaced by negative cosine of alpha. And for this right angle triangle, that AB times cosine of alpha, AB times cosine alpha give us the height difference between B and A. So we can replace this mg, and the negative sign still keeps. AB cosine alpha is that h of B minus h of A. So let's take a look. If work done by conservative force equal to negative changes potential energy, which means negative change is always potential final minus potential initial. Now let's take a look. In our case, work done by gravity equals to negative. We have this negative. See that? Negative. It looks like our mgHb should define as the potential final minus mg of HA should define as the potential initial. Therefore, potential energy related to gravity is mg of H, because final is mgHb. Final minus initial. Initial is mg of HA. This negative sign should be in front of it. Okay. And for the mass spring case, do you remember what we did? That is that a spring of constant K with a block of mass M, and work done by elastic force equals to F dot dx. Since elastic force is always at opposite direction, displacement is negative, of magnitude is kx of dx, and from a position x of A to x of B, and negative 1/2 k of x squared as the result, xa, xb. Okay, now leave this negative sign outside, and then we have 1/2 kx, the final is b, squared minus 1/2 k of initial x of A of square. So let's compare. Work done by a conservative force, which is elastic force, equals to the negative. Here's the negative. Look like the potential energy final for elastic force is 1/2 kxb squared. Initial is 1/2 kxa squared. So therefore, for the mass spring case, potential energy elastic is 1/2 k of x squared. Please note that x is displacement, or we say displacement of the block, which actually is how much the spring has been stretched or compressed. It doesn't matter, stretch is positive x, compress is negative x in our case, but after square, you stretch 10 centimeters or you compress 10 centimeters, the spring both will have the same amount of potential energy. So potential energy related to gravitational has the expression of mgh, and elastic has 1/2 kx squared. Now, there's something different. Compare this to. This is u of elastic. X is pretty clear that initially that if the spring has no compression or not being stretched, x equal to 0, so x is well defined. K is spring constant. However, this h is height of the object. Now, what is height? Height is related to the reference h equals 0. Now, you can choose anywhere as h equals 0, because if you say, I choose the floor as h equals 0, now what if this floor is at second floor or fifth floor? Well, you still can do so. So, how much gravitational potential energy does an object possess is arbitrary, because you can have any h. For example, in our classroom we have a table and it has mass, right? And what is the height from the center of the table to the floor? Maybe 1 meter, that is to the floor. And the floor maybe is on the 5th floor from the bottom of the building. But if the building is on a hill and it is a couple hundred or even more meters above the sea level, and you can even take the center of the earth as h equals 0. So as a matter of fact, MGH has not much of real meaning involved. It is the delta. It is the delta of G give us mg of delta of h, which actually means a lot, because no matter which reference point you choose, change of height will be the same for the same event. So I'm going to give you an example later.